actually leave mostly blank because now we can get horribly enthusiastic. We've done conservation of charge. We have done conservation of energy. So we say, hey, what's next? Well, momentum, angular momentum. There must be some density and some current associated to momentum. Must be some density and current associated to angular momentum. Okay, and indeed there are. And of all people to kind of do that properly, who else but Maxwell? So Maxwell defined an object, it's called the stress tensor, that you'll find in the notes. Maybe I'll just write it very quickly so I have it. But I want to emphasize this is really not stuff that I expect you to learn. Just to know it's there. So what's the Maxwell stress tensor? What's a tensor? Well, a tensor is just a glorification of a vector, but now having multiple indices. Okay, usually two indices. You know that as a matrix. Fine, call it the matrix if you want. It's a tensor. Same thing. So by definition, it's the following object. So it's a combination of different components of the electric field. Like this. And so what's the interpretation? So Tij, it's the force per unit area in direction I on a surface oriented in the J direction. Okay, so you've got a certain you've got electric, you've got magnetic fields, you've got a little surface here with a normal going in a certain direction, which is J, and then on this thing here, there can be a force in any of three directions. So the Maxwell stress tensor essentially tells you what force acts on a certain little blob like this. Okay, so I'm just mentioning its existence. The derivation of of this you'll find in the notes, but again, don't like crack your head for the exam for this, because I'm going to view this as extracurricular material as far as the exam is concerned. However, I want to say that there is essentially a kind of continuity equation associated to that. So, for example, for momentum, so continuity equation for momentum, what does that tell us? It tells us that the time derivative of g, which is our momentum here, with the divergence of the Maxwell stress tensor is equal to 0. It's the same kind of equation. This g here is just epsilon 0 mu 0 s, which you can just rewrite as just epsilon 0 E cross B. Okay, so intuitively, G is the momentum carried by the light field. It's kind of normal that it's the same direction as the pointing vector, which points to the direction of the energy flow, because you know E is equal to C times P. So there's just a kind of difference of a factor of light velocity between the two. So the kind of momentum of the electromagnetic field is given by this particular combination here. So here, I'm not going to derive all these things in there. It's in the notes, but again, just stating so you know the existence of these things. And then there's a similar thing with angular momentum that we can do that. Okay, so there's just a statement, but you see the general form of the equation is the same, except this one here is a little bit richer, right? Because we had before our continuity equations for a scalar conserved quantity, charge density, energy density. Now it is a continuity equation for a vector quantity. So this has three components. So this is really three continuity equations. And the t here is not just a vector, it's this tensor. So it carries two indices. So then this divergence here acts on one of these indices in there. So this is really three continuity equations for three orthogonal components of your momentum. Okay, but just mentioning the existence of this before we carry on. But I'm not going to insist on the derivation of this. I mean, you'd be entirely capable of following the derivation of this. It's just, once again, starting from Maxwell's equations, plugging things into the momentum of a particle as it gets acted upon by electromagnetic fields. You can follow the derivation, but I'm not going to insist too much on it. Okay? Just once again, to emphasize the importance of such equations of this form relating the derivative of some local charge with the existence of a current.